classical asymptotic analysis. I will now have, the plan is we have a series of 3, maybe 4 lectures about fluid flow in system of thin pipes. For Newtonian flow, that is a paper by Professor Maršić from 2003, I think. Then generalization by Pažanj and Bannacht in 2015 for micropolar. And then maybe I will do one lecture about power law fluids, which I don't know much about. Jean knows a lot more. But I would like to maybe go through these power law fluids in system of thin pipes. And then probably Professor Pažanj will continue with some lectures, and maybe you will have some seminars, we will see. Okay, so basically, this is like, we had this intermezzo with the unfolding method, and I'm continuing the enumeration. So fluid flow. So fluid flow in a system of thin pipes. So we are looking at today I will just be talking about the Newtonian case. Of course, there are a lot of details in all these papers that I will omit. I'm just presenting the basic ideas. All the papers, all 2 or 3 papers that I will be talking about are in Google Drive, so you can check them if you're interested. I'll just outline the basic ideas that are different from the domains that we considered up until now. So problem settings. So the paper that I will be going through is by Professor Maršić. I will just write down, so it's rigorous justification. So justification of the Kierkov law. I'm not sure, maybe it's 2H here, but okay, let's say it's like this. Kierkov law for junction of thin pipes. So filled with viscous fluid. So this was published in Asymptotic Analysis in 2003. So we talked a bit about the flows in standard, undeformed thin pipes, in curved pipes, in helicoidal domains, and now this is somehow generalization of all this. So we are looking at the most natural setting, that's a system of thin pipes. So we need to introduce the following notation. So you have omega epsilon, which is basically a union of m+1 sets, so omega epsilon I, where this omega epsilon I, there will be a lot of this different notation because you need to consider near the junction, away from the junction, as a whole. So it's a bit, maybe notation is a bit confusing, but it's the best that you can do. So x1y, x star I from R3. So x1 is from 0 to L1. X star is from B epsilon I. Okay. So here this B epsilon I is epsilon Bi, where this is of course a circular domain, so Bi. Of course it doesn't need to be, but it's for some computations it's much, you can obtain explicit expressions, so So this is the, I think it's written like this, I've pipe in the system of pipes. Okay, so I is between 1 and m. And now, of course, in each of these pipes, they do not need to be of the same, so this bi can vary. So you can put a different coordinate system in each one of them. So for each pipe, but they all need to be of order epsilon, otherwise your computation won't work. So for each pipe, we can use a different coordinate system. So you can denote it by this, EKI. So K is, of course, 1, 2, and 3. And I is 1. So these are three-dimensional pipes. So it can be done in this general setting. Okay, what else do I need? So, of course, this epsilon is a small parameter. That's the diameter of the pipes. So small parameter. And then you have the junction of pipes, omega epsilon 0, which is also of order epsilon. So it needs to be of order epsilon, where omega 0 is some bounded domain, and there are some other technical details which I won't go into. If you're interested, you can check the article, the paper. So this is the junction of pipes. So your domain looks something like this, for example. Okay. So let's say we have omega epsilon 0 here. So you will have a solution here in the junction of pipes. In these pipes, it's well known that you need to have a Poisson flow, at least when you move away from the junction. So somehow you will need to find this solution, the solution of the Poisson, and somehow match them in some way, so that your error estimate is as good as possible. So you will need to define a correction on these interfaces, which will be of order here, of order epsilon. I think ln of 1 over epsilon, we will see, times some d, which will be connected with the pressures. So it's some constant. So yeah, there's also a bit of technicalities behind it. Why exactly this? Because the result for the exponential decay gives us this, and the existence of exponential decay gives us exactly this value. So the lateral boundary. The lateral boundary is given in this way. So you have x1i. This is more or less standard. R3. x1i is from 0 to L1. And the x, I have star down. X star I is from this boundary. Okay, and you don't have, as usual, like two ends of the pipe, but just the M exterior ends. So you have the exterior end. Which is given in this form. So sigma epsilon I is just Li x star I, which is from R3. Okay, and you can denote this lateral boundary. Is basically the boundary of the domain without the exterior ends. Okay, so this is more or less clear, I think. So this is your domain setting. I think it is quite natural, nothing out of the ordinary. If you've never seen stuff like this, maybe it's a bit new, but it's quite natural how things are defined. So the equations are, of course, we're looking at a viscous fluid, so you have Navier-Stokes, so minus my time Laplace u epsilon plus the nonlinear term plus gradient p epsilon. Here is just 0 on the right hand side, and omega epsilon. The divergence is 0. U epsilon is 0 on the lateral boundary, and you have this standard condition. This is one way you can pose it. So you have the cross product of U epsilon and E1 to be 0, and P epsilon is Pi. So you have the pressures given on the exterior end. So this is all you can check in the paper, but it was, I think we also had this kind of condition before. Maybe not, I'm not sure. So this is called the Saint-Venant principle, that at the inflow of the domain, the most important part is the velocity in the direction of E1. So the other two components can be neglected. Okay, so let's denote this by 1. And just comment on the well-posedness of the problem. So we have a problem like this, 4, 1, 2. It's more or less standard, but I'll just outline the basic idea. There are different ways how you can address it. So well-posedness. Of the system 1. Okay, so I will introduce the natural variational formulation. So you have this way. So variational formulation, find epsilon, which is from V epsilon, which will be the space of functions that are H1 omega epsilon, such that they are, of course, 0 on the lateral boundary. The divergence is equal to 0 and omega epsilon, and you have this condition satisfied, so U epsilon times E1 I is 0 on sigma, so on the exterior ends. So find this such that the following holds. So you have the following: me integral of omega epsilon gradient u epsilon gradient psi. So you have phi, sorry, plus integral of omega epsilon. So it's a very classical variational formulation. So here you have, you just need to be careful because you have m pipes. So here you have the sum of pi and the integral over the exterior ends. Okay. So we have this variational formulation. I will introduce this di, which is pi minus q, q being the mean pressure. I will mention this a bit later, so mean pressure. You will see why this is important. So the result is obtained by using the Bannacht fixed point theorem. So let's see the assumptions. So we have the following theorem. So let this d be the square root of the sum di. So let this be the let's say the total pressure drop. So you need to have this total pressure drop times epsilon squared is, let's say, small enough. So this is, of course, a technical assumption that you need for your proof to go through. So if the absolute value of d and epsilon, which is the small parameter in the thickness of the pipe, are such that so epsilon squared d is less than me squared over 4 c2 squared c1. So c1 is the Poincaré constant, should be, and c2 comes from the embedding theorem in L4. You can check the details, as I said, in the paper. So I can write here. Then the system of equations. One has a solution. Of course, you have problems. You have this nonlinear term, a bit of problems with the uniqueness. However, you can assure that such a solution is unique. Maybe we talked about this before. I'm not sure. I think we did. Such a solution is unique in the ball. I think we did when we did the paper by Professor Pajan in the three-dimensional pipe. So in the ball, the epsilon so this is the space of functions such that their gradient, of course, they are from the epsilon, is less or equal to mi over 2c2 squared epsilon. So this I can write down. So this is Poincaré constant. and this is from embedding. In L4. Okay, I will just outline the idea of the proof. So we use the Bannacht fixed point theorem. So you define the following. So define some t from b epsilon to b epsilon as t of v is u, where this u is the solution of the variational problem. We already had this basically, but let's recap it. So find u in v epsilon such that, let's just denote this by 2. So this is free. So you had this variational formulation, but let's recap. So me integral of epsilon. So this is from the Laplace, from the nonlinear term. Plus the sum of pi and the integral over the exterior ends. So it's going in this form. For any function from v epsilon. Okay, so the idea of the proof is threefold. I think it's more or less standard. So it's about maybe 1 page long. You can check it. I think it's good for exercise. So idea of the proof. Idea of the proof is the following. So you first need to define that t is, you need to prove that t is well defined. B epsilon, so you have elliptic quadratic form, so you need to check this. Then you need to prove that tb epsilon is the subset of b epsilon, and that t is a contraction. Okay, so if you have all this, it's a bit of work. So the Bannacht theorem implies the existence and uniqueness of u epsilon. Z. Ah, sorry. let me just check just a sec. It's yeah, we should be present here. Okay, so this is one way you can prove this thing. The other one is a bit, well, it's from a mathematical perspective, it's of course justified. From physical, not really. So you use, I think I mentioned it, how do they call it? I think the artificial pressure, so Bernoulli's pressure. So let me just mention this. So this is if you have problems with the energy inequality, you introduce stuff like this. So you can find, I think Professor Poloka did a couple of remarks on this if you're more interested. So it's a bit also quite technical. So existence and uniqueness. Using Bernoulli's pressure. So Bernoulli's pressure P plus 1 over 2 U squared. So there are a couple of papers with this. One that is quite often cited. I'll write it down, just the authors. So Conca, I guess it's called Mira, and Pirona. I think I mentioned this paper, but it doesn't hurt to mention it again. So it's called the I think I put it in Google Drive if somebody is interested. Not sure, but I think I did. The Stokes and Navier-Stokes. Equations. So with boundary conditions. Involving pressure. So this is from Japanese Journal of Mathematics. Maybe Jean, you know something about it. Yeah, anyway, so it's from 1994. Okay, so this is an alternative method to use. Okay, so this is a bit about well-posedness, and now I'll talk a bit about the asymptotic analysis that we are mostly interested in. So of course you need to take a bit of a different approach here. So you will have a flow far from the junction and near the junction. Near the junction you have the so-called Lee-Ray's problem, which has been extensively studied in the case of viscous fluids, and more particularly the steady flows. The non-steady flows were mostly done by a number of authors, but recently by Professor Pileckas. He did a whole series, I think, of papers on this. So for the non-stationary, you have different kinds of problems. But for the steady cases, mostly it's the main reference is Galdi, who I mean the book, of course, who studied in a variety of settings. Okay, so let's put like this, 413. Of course, these Lee-Ray problems are not just important for system of pipes, but usually you get them when you are studying the boundary layers in the problems for the boundary layers in the ordinary undeformed pipes. So first you have this Poisson flow, which we know everything about. This is, let's say, far from the junction, in some sense, so far from the junction. Okay, so we have the following. Let's write like this: U epsilon I. I'll just write the solution. So U epsilon I is epsilon squared. So this calligraphic U of x. And it can be computed. I will not provide the computations, just the formula. So epsilon squared Vi of x star I over epsilon over Li. Q minus Pi E1I. Okay, so this Q is the constant value of the pressure at the junction point. Okay, and P epsilon I is 1 over Li. Of course, this Li, Pi are for the corresponding ith pipe. So this is pi I minus Q x1I plus Q. So this Vi so it's the solution of the auxiliary problem. On the cross section. So I'll write it down generally and then write down the explicit expression for when the cross section is circular, which is the problem that we're interested in. So auxiliary problem on the cross section. So you have the following: minus me Laplace Vi is 1, Vi is 0. So this is in Bi, and this is on the boundary of Bi. Okay, so in the case of circular pipe, you can obtain that this Vi of y is 1 over 4 me Ri squared minus the absolute value squared of y. So this is the case of circular pipe. Yeah. Of course, you can everything can be expressed in terms of a, let's say, arbitrary cross-section, not really arbitrary, but in some sense. But we like to do more for the specific circular section, since it is usual. So. Okay, so regarding the pressure, it can be standardly recovered from the divergence condition. So the pressure Q is computed from 1, 2, which is, so it's divergence U epsilon is equal to 0 in omega epsilon. So you get that 0 is the sum of 1 to m, the integral over the exterior ends of u epsilon I times E1. So use the divergence theorem. So we can denote this by 4 and this by 5. Okay, and now plugging four into 5, you obtain the following. So of course this is for the case of circular pipe. So Q is the sum. So as Q is the sum of 1 to m, 1 over Li, Ri to the fourth, Pi over the sum I 1 to m, 1 over Li, Ri to the fourth. Okay, so this is how you recover Q. Let me just have two remarks here. So you can write this. So remark 1. So identity 6. So we call the identity six. It's called the Kierkov Formula. It's the analogy with electrical circuits. Since the modeling of electricity and fluids, there are some comparisons. So we call the identity 6 the Kierkov formula. So it's analogy with electrical circuits. Okay, and remark 2. So if Ri is equal to R, Li is equal to L, then for every so I, which is from 1 to m, so this means that the pipes, which is not that unusual. We are working in a general setting, but let's just say the pipes have the same radius and length. So then from 6, we obtain that Q is 1 over m, so very simple formula. I is 1 to m pi. Okay, I would have a 10-minute break now, so we continue at 11:05.